Now we have got good idea about inductors and coupled inductors. So now let us look into how to design capacitor on chip. As we have already seen in a CMOS process, we have access to multiple metal layers. So these multiple metal layers can be very easily used to design parallel plate capacitors. The simplest way to do is we can just take two terminals out, take these two, and these two metals will be having some spacing. In addition to that, you can easily imagine that they will be having some overlap area. So this is a simple parallel plate capacitor. We can see this electric field between these two parallel plates, which will store the energy. Now, one thing to note here is that this spacing is very comparable to the thickness of these metals. So we are also going to get good amount of this fringing electric fields. C will be having this parallel plate capacitance plus this C fringe. The parallel plate is just based on the overlap area, but this fringing capacitance also is going to be substantial value. Now, when we are trying to design a capacitance on chip, we have to also worry about the overall area it is going to take. So since we can see that there is this extra fringing field which are available, which gives rise to this fringing capacitance, why not to also maximize the utilization of this fringing field? So this can be done by splitting the metal into this kind of thin strips. What happens now is we not only have this kind of electric field, we also have substantial amount of this fringing fields, and we can just create like this, and then we can replicate the structure. And to further improve the capacitive density, what we can do is, if we are choosing this as, let's say, P1 and this as P2, the neighboring strip we can choose to be P2, and then here we can choose P1. So now this is going to increase the overall cap density which we can achieve. And similarly, P1 and P2. So we will be alternating between P1 and P2 as you move in the same plane. So here, plates are converted into thin strips to increase fringe capacitance. And this idea can be extended to more than 2 layers. So you can add as many layers as you want. So this is, and you can already see that this capacitance is formed just by using the metals which are available. And this region between these metals is filled with oxide. So this is also called as metal oxide metal capacitor. MOM capacitors. These MOM capacitors, as we can see, by utilizing multiple layers, we can achieve good density. So here we can get a density of around 1 to 2 femtofarad per micron square. When we have, let's say, 7 to 8 metal layers available. Another good thing is these capacitors are very linear and they have a decent quality factor. But at this few gigahertz range of frequencies, we will find that the quality factor of these capacitors are much higher than the quality factor of inductor. MOM capacitors, linear, Q is better than inductor. This is, and this doesn't require any special kind of fabrication process. Available in all types of CMOS technology. Okay, so here we saw that one way to increase the capacitance density is by adding a lot of such strips in the same plane as well as in different layer. But from our understanding about the parallel plate capacitance, we know that this spacing is very crucial in increasing the cap density. So if we have two metal plates and each of them, let's say, have an area of A and a spacing of, let's say, T, and the spacing is filled with some material having a dielectric constant, then we know that this C is equal to A by T. Okay. So if you want to increase the capacitance, we can either increase the area, and this increasing area comes with a penalty that overall on the chip we are going to consume more area, or we can reduce its thickness. Now, in the standard process, this thickness will be decided by various other parameters in terms of how reliable will be the interconnection when the dielectric between the metallizations are very thin. And this epsilon r is again kept as low as possible in a given process because we want to reduce the coupling between the two metals. So many times this epsilon r will be just a silicon dioxide which has this relative permittivity of around 4. But let's say we have an application where we want to maximize the capacitance density. What we can do is for a given area, we can increase epsilon r and try to reduce this T. And this is possible in some of the specialized CMOS process, which are tuned for this kind of RFIC design. So what is done is I epsilon r insulator is sandwiched between two metal layers. So these metal layers are not used for routing, special metal layers. And I should also emphasize that high epsilon r insulator, which is very thin. With the help of this special metal layer and this insulator, we get a capacitance, which is also very dense. This is called as metal insulator, metal capacitance, or MIM cap. The MIM caps are not available in all process, but whenever it is available, it has this property that you can just use two special metal layers and get a good amount of cap density. Talk about the properties of this MIM cap. This can also provide density which is similar to that of MOM cap, but one good thing is this MIM caps can be fabricated much above the substrate. MIM cap linked to substrate is so it has the benefit that the substrate coupling is reduced, so any noise in the substrate or loss in the substrate automatically gets reduced. And this way also, the way we can see, it's highly linear. Many times the cap density which we are getting, this 1 to 2 femtofarad per micron square, is not sufficient, and we want even higher cap density. So this can be achieved by knowing the fact that when we are designing this MOSFETs, this gate oxide is very, very thin. So the typical cross section of an NMOS will look like this, where you have this gate oxide. Then this is the gate material added on top of the gate oxide. Gate, let's say this is source, this is drain. The gate oxide will be many times it is just a silicon dioxide, but there are also new processes where this is a specialized high dielectric constant material. This gate oxide can be very, very thin compared to the other interlayer dielectrics. So as a result of which we can achieve much higher gap density when we are using this as a capacitor. So if the gate is used as a top plate of a capacitor, and when the MOS is biased in inversion, then we can see that this channel will act like a second plate of the capacitor. So we can try to utilize this structure to design a capacitor. We know that if we apply gate bias, so this VGS, and we try to measure the capacitance between the gate and source. So this capacitance is going to be very low when the gate source bias is also low. But as we increase the gate source bias, this capacitance increases because of inversion. Similarly, when we reduce the gate source bias, there is an accumulation which again causes the effective capacitance between gate source to increase. In between, because of this extra depletion, the capacitance is going to fall. But as long as we are operating in this either inversion or fully accumulation region, we can obtain large value of capacitance between gate and source. So this is the motivation behind using a MOSFET as a capacitor, also called as MOSCAP. You can see it can really have a very high cap density. You may get of the order of 10 femtofarad per micron square. The downside is, as you can see, it's nonlinear in nature. Also, we will see that the quality factor of a MOS cap is not as good as the quality factor of a MIM cap or MOS cap. But still, it is extensively used whenever we have a high cap density requirement. So when using MOS as a capacitor, it is better to short the source and drain together to form the second terminal. So this is gate, the source and drain are shorted together to form just another terminal. So one practical use case of a MOS cap is in creating supply bypass gap. So since the supply is always going to be much higher compared to the ground, so source and drain of the MOSFET are grounded, and the gate is connected to the supply. It creates a good bypass capacitance between the supply and ground. Here, an NMOS is used. Now, cases when, let's say, the capacitance which we want to form is connected to a node which is much lower than the supply voltage. In such a scenario, we may have to use a PMOS, and this PMOS source drain in turn are connected to the supply. Is, let me call it VLOW. So for such a scenario, this PMOS can provide a good capacitance between this node to the supply, which is also an incremental ground. And NMOS normally will not be able to provide a high capacitance when the VLOW is not very high compared to the threshold voltage of the NMOS. PMOS as bypass cap when VLOW is in other applications. This can also be used as a two-terminal device, but we have to be careful in making sure that these MOSFETs are biased in appropriate inversion region. The on-chip capacitors are fabricated on top of a substrate. So these metals will be, let's say, here. Similarly, this MIM capacitor can have a specialized layer. So these are metals. These are MIM layer. So all of these will also be having some coupling to substrate. So as a result of which, when we are modeling this capacitors, so this on-chip capacitor will have, first of all, some loss, which can be modeled as, let's say, series resistance, which is coming as a result of the resistance of these metals which are used. In addition to that, there will be this coupling to the substrate. Let's call it C. Then you have this capacitance and then some loss. In the case of a mom cap, this capacitance from the bottom plate to the substrate can be pretty high as compared to the MEM cap. So because of this coupling to the substrate, the desired effect of this capacitance may not be achieved. So many times design is done in such a way that when we are using just a mom cap, either we use the layers from the top metals or we just go with the MEM cap. So mom cap is higher substrate. You can always use just the top metals for designing a bomb cap, but then we lose on the cap density. So in such a scenario, this MIM caps can be very useful. One downside of a MIM cap is it also is very sensitive to the antenna effect during fabrication. So if we are not careful, then this thin dielectric of the MIM cap can break down during fabrication. So we have to pay extra attention in designing the MIM cap so that the antenna effects doesn't come into play. Let's talk about resistors. in CMOS process. So we know that this process provides various metal layers. So one simple way to realize the resistance is by just connecting the two terminals of a metal wherever we need to use a resistance. So the resistance of such a metal resistor is going to depend on R will be the resistivity, the length, and the cross-section area. L, see the cross-sectional area. So this area can be determined in terms of thickness and width. So L by T to W. So when we are using the CMOS process for designing this resistor, so this resistivity is not in our hand. Also, this thickness of these metals will also be predefined. So if we are using some specific metal layer, that metal layer will have a thickness, let's say, of 0.2, 0.3 micron. In designer's hand, you have this length of the metal which you want to use and the width of the metal. So these two quantities are fixed by the foundry. So many times what is done is this rho by T, rho by T is separately given by the foundry as the material thickness is predefined. So this rho by T, you see, also has a units of ohms, but when length and W becomes equal, then the resistance of such a material is going to be equal to this rho by T. So this is also called as sheet resistance. Resistance and denoted as R with a square box here, showing that if the top view looks like a square, then the resistance of such a block is going to be equal to rho by T. It has units of ohms per square. So when we are trying to design a resistor, it is very convenient to just know the sheet resistance. So if you know the sheet resistance, let's say it is 1 ohm per square, then I need to have length which is, let's say, 10 times of width to design a 10 ohm resistor. For metals, we'll see in CMOS, this R square or the sheet resistance is varying in the range of 0.1 to 1 ohm per square. So which is really low. And if we really want to design a high resistance, using this metals to design resistance is not practical. To know most of the applications. So in addition to metals, some other materials are also available in CMOS process. So we can use polycrystalline silicon, which is available in a CMOS process. So this can be deposited above the substrate So the heat resistance of this polysilicon material depends on if extra silicide process has been applied on this polysilicon. So if it is a regular polysilicon without silicide process, then the sheet resistance will be of the order of 1 kilo ohms per square. Whereas if we say silicide polysilicon, the sheet resistance will have the order of 10 ohms per square. There is another way to realize resistor on chip, that is by using the diffusion. So we already know this diffusion is done to add N-type or P-type pockets in the substrate. We can use these diffusion regions to also realize resistance. Diffusion resistances, we make this contact, let's say this is an N-type diffusion. Here we see that since the substrate is already P-type and we are adding an N-type diffusion to this, so there will be depletion around the external surface of the diffusion resistance, and this depletion will decide the effective cross-section area in which current can flow. So effectively it's forming a PN junction. You can already see that this PN junction, this depletion region width will depend on what is the voltage which has been applied. So let's say it is a higher voltage, this is lower voltage. It means there will be more reverse biasing here. So the depletion region will widen in this region. So as a result of this changing in the effective cross section in which the current can flow, we will also change the effective resistance of a diffusion resistor. Diffusion resistors. Effective cross section depends on, which means it's a non-linear resistance. So for diffusion resistance, we can get a sheet resistance of the order of 100 ohms per square. So this diffusion resistance can be useful in many applications as long as we know there is no strict requirement on the linearity. Now we have seen these various passive devices which are available in a CMOS process, like inductors and mutually coupled inductors, capacitors, and resistors. Now we will look into how to utilize these devices to design useful circuits